All right, welcome everyone. We can go ahead and get started while the last few people. Hello.
Hello.
Hello. All right, so we're gonna go ahead and get started. Hopefully everyone's enjoying the pizza. There's a sign-in sheet that is going around. Please sign in. That of course helps with the pizza. So I think most of you guys have been here before, so I don't really need to give too much of an introduction to the seminar series itself. So we'll just go on with our speaker. I'd like to introduce Xin Rong, who is a PhD student in the School of Information, and he's going to talk to us about some deep learning models.
Hi, everyone. Glad to be here. I'm Xin Rong, and thanks for the introduction. I'm still a PhD student for a couple of more months. Hopefully, everything goes smoothly. I get out here around April. So today, I'm glad to talk about interactive programming tools powered by deep learning models. Today's talk mainly consists of two parts. Where should I point this? It was working 1 minute ago.
Last week.
I'll just use the keyboard now. OK, so the first part is the main thing I want to talk about today, CodeMend. It's a user interface powered by bimodal embedding model. On the back end, it supports user to find code examples and modify code snippets using natural language. And the second part is a work in progress project, image to code. It allows the user to use visual examples like images to find code examples. And it also involves neural networks synthesizing code examples on the fly.
Should be okay.
Oh, yeah. OK, so the first part. So this is a paper I presented at a User Interface and Software Technology Symposium this past October in Japan. So the motivation for this project is that we want to help user program more easily. So there are two specific problems with programming that we identify to be especially difficult for users, especially novice users. The first one is that there's often a lot of APIs involved in end-user programming, and it's really hard to navigate through these APIs and with a lot of functions and parameters and values if you're not familiar with those. And also, it's often hard for a user to translate something that they have in mind into the actual API call sequences or actual code snippets. So in this project, we focus specifically on one type of programming, interactive programming. By that, I mean the kind of programming you do with, when you interact with IPython notebook or R or MATLAB, where you can write a piece of code and edit it, and we'll see instant a result or preview so that you can iterate very fast and get insights into data. So I'll show you first what we built by using a video demo. So two things before showing the demo I want to mention. First is that we built this system for one specific library, matplotlib. It's a Python library commonly used for plotting figures. And also in this video, I want to assume that the user wants to create a bar chart that looks like this one. So it's a toy example, but pay attention that the bars are red and there's a title on the top. So let's see how the user modify a generic example to something like this. Let me roll the video. OK, so this is the interface of the system we built. It's called CodeMend. On top left, there is a code editor. Bottom left is image preview. We will see it in a moment. And this is a query box where the user can enter natural language queries. And here's a list of functions and a multi-functional display for recommending code modifications. So suppose the user wants to create a bar chart from scratch. The user can simply type in a query, create a bar chart. So as the user types in the query, the system automatically finds what functions are relevant to this query and rearrange these. The color represents the likelihood that a specific function will complete this will fit the user's intention. The user can click on the highlighted function. And what the system will do is to show a list of code examples, images generated by the code examples found online. So these code examples are crawled from Stack Overflow, from GitHub, and other tutorial pages. And the corresponding images are nicely laid out here for the user to preview. The user can click on any of the image. The corresponding code example is automatically populated into the editor. And the user can also see a preview of what is generated by this source code. So now suppose the user wants to change, let me see, the user wants to add a title here. The user can type in, I think, add a title. So again, as the user types in the query, the system automatically re-ranks the most likely functions based on this query, and then highlights, use color to encode the likelihood. Again, the user can click on the title, the highlighted function. This time it's different because it involves inserting a new line of code, and rather than creating something from scratch. In this case, the system shows a function preview and also the suggested parameters for this function. Here, 0 means the first non-named argument of the function. The user can click on the suggested function, a parameter, and also click on suggested values. So again, these values are crawled and counted based on the code examples found online, and they are ranked by their frequencies. So the user can intuitively see, what kind of possible values are for each suggested parameter. The user can click Insert. The system will automatically figure out the best position to put that line of code into the existing code snippet, and the video preview is also, image preview is also automatically updated. Now, suppose the user wants to change the color of the bars. The user can type in, change the colors of the bar. Now, what's different this time is that it's not inserting a new line of code, but it's modifying an existing one. So the system will highlight which line in the existing code snippet should be modified. Again, this is using color encoding. When there are multiple lines that are likely to be modified, then multiple lines will be highlighted. In this case, there is only one. The system can click on the suggested line, and it will pop up a list of suggested parameters for the user to modify. The user can click on the suggested parameter, which is color. And here, the values are for this specific parameter. These are ranked by the frequencies that are used in the code examples found online. The user can click on the suggested value and hit Update. The code is automatically changed, and so is the image preview. So this way, the user completes 3 tasks: creating something from scratch, inserting a new line of code, and modifying an existing line of code. So there are more complicated examples I will now show here, but instead I would dive into a little bit more detail on how this works. But any questions before I go on?
Yeah, there's a lot more colors available. Is it any way you can get those easily?
Well, it really depends on the collection of the code examples we have. Say there are 55 distinct colors used in the existing code examples. That's what we're going to show in the interface. But it's if we want to throw in more engineering effort, we can build a color palette for users to choose, and RGB values, whatever. Is that?
Yeah, I know they're in the library.
Right.
There's a defined set of ones by names, plus you can do RGB values.
Right. Yeah.
And another question is, so how do you build a database? It's just like you write a web scraper to download all the GitHub and Stack Overflow.
Right. So Stack Overflow, for different things, we took different strategies. For GitHub, we searched for those repositories that contain matplotlib, the keyword matplotlib, and then we filtered those whether they actually contain runnable code examples. And for Stack Overflow, we just looked at the tag of the questions. And then from there, it's pretty straightforward to collect a whole bunch of code examples.
So the problem is sometimes, especially for Python, people will import in different style. usually people who like from matplotlib.py import matplotlib.pyprog as PLT.
Right.
And what if another person from matplotlib import pylab?
Right. So there is some normalization going on in the code preprocessing. I will talk about it in a minute. But like the general idea is that so we normalize the different variable names to something more canonical, and the system can identify that this module is matplotlib.pyplot, no matter what. Regardless of what name people give it. Yeah. So we can revisit that issue in a minute. Okay, so yeah, so in that video, just a quick recap, I showed 3 types of programming operations. Scenario 1, create something from scratch. Scenario 2, insert something new. And scenario 3, modify an existing line of code. And we want to build some kind of black box that supports all 3 scenarios. And in existing literature, what was explored a lot was really the first scenario only, which is you find some, you have some natural language query, and the system can find your code examples. So traditional solutions, people can Google or search for things in Stack Overflow. And in the software engineering community, people have invested a lot of effort into so-called code search or programming by example. And in the natural language community, people have also looked at natural language-based code synthesis. But again, like I said, all of these were focused on the scenario 1 instead of more nuanced operations where you need to not only understand the intent behind a natural language query, but also the context of the code example. So we think for this particular problem, for building this black box, deep learning is a good fit. For a few reasons. First is that it's relatively simple to use, and that doesn't involve a lot of human engineering efforts to code up the features. It also is good for transfer learning. If you provide a lot of data, in one domain, it's good. It has the capability of, adapt it to a different domain. And in this particular case, if we have a lot of natural language text about Python in general, it may be capable of adapt the relationship learned from there to code specifically related to matplotlib. And of course, more data and a deeper structure will always lead to better performance. And very likely, we do have a lot of data for this problem. So online, like I said, there is Stack Overflow data, GitHub, and a lot of tutorials, textbooks, and the massive online course data that involve code examples. So how does this work? It really involves building this black box that supports natural language and code as context and code suggestion as output. And in order to train this kind of black box, you need 3 kinds of data: a lot of natural language talking about the actions that the user wants to take, a lot of code examples, and what's more important is the association between natural language and code. So in reality, here's the data, the kind of data we crawled. We, from Stack Overflow, GitHub, and tutorial pages, we collected more than 50,000 code examples, all related to matplotlib, and over 90 million words in the text corpus mentioning about the actions about this library. So now comes the most exciting part, which is to open up this black box and see what's inside. And inside this black box, we use a so-called bimodal embedding model. Bimodal means it supports 2 modalities. One is source code and one is natural language. And again, the task for this model is to, given the 2 concepts, predict whatever output that can be used to render in the user interface. So there are 3 specific problems in adapting this model to the actual problem. The first problem is that given any raw piece of code context, how do we map it to the model input? Here, it's really a lookup dictionary where there are one-hot vectors representing different code elements. So which I will talk about this mapping in a minute. The second problem is, given a natural language query, how do we map that to the model input. And third problem is the model's output is a multinomial distribution. How do we leverage, first, how do we define the elements in this distribution, and then how do we map that to the user interface? So let's look at these problems one by one. The first problem is how to map source code into this lookup dictionary. So so the source code here can have a variety of structures, but then we take the abstractions that each source code corresponds to our abstract syntax tree. So the abstract syntax tree can be further broken down or flattened to sequences of a set of so-called code n-gram representation. You can understand each n-gram as a complete path or partial path from the root node of the tree to some internal node or some leaf node of the tree. So this way, we break this tree down to a set of words, you can say, or n-grams, and these can then be mapped to this lookup dictionary. Any question about this? So for example, here there is a function call, module function parameters values. The representation I created was the function and the parameter, the function and another parameter, and so on. So we think this is a signature that represents what this code means, and it can get more complicated. Like there are like chain function calls. So then the tree gets more complex here.
So these complicated structures, don't they significantly increase your?
Yes, it makes the data space very sparse. But that's one thing that the embedding model like this one, the lookup table, is actually good at handling. So the space is quite sparse. I'm sorry? What is? Oh, 0 here. Yeah, it means the sort of the zeroth, the first non-named argument. It means that this particular argument is present in the function call. Yes.
You maybe mentioned this already, but do you also bring in like the API documentation so you know all the possible things that can be put into one?
That's right. Yeah, we do bring in API documentation. Okay. Yeah, and actually it's useful further down in the task. I will mention in 2 slides down. Okay. Yep. Okay, so now we are able to map any given piece of source code into a lookup table. And now let's look at the natural language part. So this one is actually much simpler. A lot of existing solutions just simply use so-called bag of word representation. Given a natural language sentence, we just break it down into a set of words in the sentence, and then these can be very straightforwardly mapped to the dictionary. But there is a problem, a problem with this. But there is a problem. So in model when we are training a model, there's actually no such natural language query for us to leverage, right? We only see code examples and API documentations. So what we need to do is a step called API documentation lookup, where we generate these simulated natural language query from the code examples, and in specific from each code element, like module, function, parameter, and value, so that we simulate what the user might ask for given this code example. And so this is sort of function as a surrogate of the user intent. And during model deployment, we naturally have a user issuing those queries for us. So we don't need to worry about that during deployment. Okay, the third problem we want to address is the user interface. So this bimodal embedding model has these part as input, and it has these internal representation of the code elements as embedding vectors, and then they are concatenated as a hidden layer. And then this is a softmax layer that generates a multinomial distribution. So the problem is, given this multinomial distribution over all possible code elements, here a code element again can be module, function, parameter, and value, there's you can imagine this is a distribution over all of the possible elements. This is one of the example. How do we display it on the user interface? It is a design issue. So we take inspiration from this so-called spotlight search interface on Mac. If you have a Mac, you type in the system preferences, you type in a query. It shows all the possible solutions at this given moment, given this partial query. We think this is a brilliant solution for addressing the ambiguity in the user's query, because the user can not only see the possible solutions for the current partial query, it also shows all the other options. All the other options are still there. They don't disappear. So that the user, if they mistype something or miss something, they can directly see all the other alternative options. And it really gives the user a lot of flexibility and convenience to find out what is possible at any given moment. And we want to adapt that idea. But there's a problem. Sorry, still getting used to this. There are tens of thousands of possible code elements in here. And we cannot afford to display tens of thousands of elements in here. It will really clutter the screen space. But there's something we can leverage. So there is a hierarchical structure in this lookup table. Remember, there are modules, functions, and parameters. They naturally fall in a hierarchy. So we can leverage that hierarchy to redesign this spotlight search. And we developed something called nested layer spotlight search, where given an expected multinomial distribution, we first show, in the first layer, we show the functions. And then once the user click on the function, it expands to the next layer, shows the parameters, and expands to the next layer to the values. And then the user can navigate through these. Again, there's a natural language query box on the top, and then the user can complete that query. And as the query is completed, the distribution is changed here. And once the user makes change on a lower layer, the change will automatically be back propagated to upper layer and then to upper layer. And this way, it's sort of folds back and integrate the solution back to the code editor. So we want to test in reality how well this works. And there are really two parts that we want to test. First is that how well does the model work, the bimodal embedding model. We adopt the information retrieval style analysis to do that. And also, we also want to understand how well does the end-to-end system work. We use a lab user study for this purpose. So let's first look at, yeah, go ahead.
Before you go into that, so how do you train that thing? So I understand that you get as your training sample
Right.
would be a piece of code, then a simulated query from this piece of code.
Right.
And as the answer, what would be?
Right. Yeah. So when we train, it's actually displayed in this page. So we collected a whole bunch of code examples,
Right.
and then we used code example and the API documentation to generate simulated queries. And then in the training time, we feed in the code context, which is a bag of code elements, and here the simulated query, a bag of natural language words. And then we have some expectation on this side, and the expectation is corresponding to whatever code elements we selected to generate the API to generate the simulated query. So this one links backwards to the process of generating the simulated query, and this way we do back propagation to train the model.
So, but then the same code is also serves as an input to your code embedding, or no, or it's a different piece of code, because in that case you would be overfitting, because if it's,
well,
you know what I mean?
Right. So that's right. That part I really didn't mention in this in the talk. So it's to avoid overfitting. If we expect this code example here, then we randomly turn on and off the other components in the code example. So that means we simulate, the user. The user could want to add this particular line, so that we make that line missing, in that code context. So it's a random process, and it involves multiple iterations to try different combinations of on and off for the API calls. It was a great question. You had a question? Oh, okay, sorry. Yeah, so let's dive into the first experiment where we want to use sort of IR style benchmark to study how well the model works. It really boils down to how well the model can rank the expected result among all the possible candidates for code modification. So this is how we set up the study. We have we know the API documentation fairly well, but what we don't know is how the user will actually issue what kind of queries in reality. So we go to Mechanical Turk. We present them with a pairs of images where there are slight changes between the image. We know what code generates which image, and we ask the user the Mechanical Turker to provide queries like this one. So the description would be how image A can be changed to image B. And one example is change the color of the bar. And like any Mechanical Turk study, the quality control is really difficult. We had collected a lot of noisy cases where they say image B is more beautiful, and we threw these away, of course. So overall, it's a very small scale, 360 queries, 61 queries collected for 5 image pairs, and we threw them to the model. So say, for example, this is an input query, and this is a ground truth, because we know which specific element corresponds to that change. And if we look at where this expected ground truth element is ranked in the model output. And here's the result. The key thing to notice here is the mean reciprocal rank for the bimodal embedding model. So this actually means that the expected results on average is ranked on a 4th place. So it's the inverse of this number. So it's not as bad as it looks at 0.2. You see, it's very low. It's actually not as bad as it looks. And another thing to take away is that when we take away the natural language context, which is code only, the ranking gets really worse. And when we take away the code context, which is natural language only, the ranking is also worse. So this means that both types of context information are useful in the model. Let's look at the second experiment where we test how well the end-to-end system works. We performed a lab user study where we had 20 test subjects. We give them a short tutorial of the system, and we provide them with a piece of code and an image generated by this source code. And then we give them a so this is called starting point image, and then we give them an ending point image. We ask the user to figure out how to change this code snippet to a new code snippet that generates this ending point image. So for example, like this one, there are always like 3 small changes that to be made. Like you want to make the padding larger, you want to change the color of this title box, and you want to rotate this pipe by 90 degrees counterclockwise. So a lot of these small challenges to be solved by the user. There are 2 conditions. Treatment condition is that the user can see CodeMan and also Google search results. And control condition is that the user can only see the Google search results. The Google search results are sort of embedded in our interface right below the suggested code changes, so that the user doesn't have to leave that page to actually open up a different web browser. Yeah, so this is what it looks like. Here is the system suggested changes, and here's the Google search results. In condition 2, the user can only see the Google search results in the lab experiment. So here's the result. Again, we have 20 participants. On average, in condition 1, using CodeMan and Google, an average user completes a task using 108 seconds. Condition 2 is 134 seconds. So we can claim that this is shorter, but the result is not really statistically significant. So that we hypothesize that this is because of the large variety of the coding skills recruited by us from School of Information master students. So then a larger scale experiment or more scrutinizing, filtering of the test subjects will potentially alleviate this issue. And in the post experiment survey, 70% of the users agreed with the statement that code efficiently helps me solve the assigned tasks. And we also collect some open-end feedback, and this kind of feedback is very dominating the pool of feedbacks we obtained. The user says, I like that it provides a comprehensive survey of commonly used parameters to functions. It really helped me, with navigating the parameter space. It's something that Google doesn't or can't do, and is helpful. So we think this is very encouraging. That the user likes this function design.
All the testers naive as far as Matplotlib goes. They've never used it.
Well, no. Like I said, there's a wide variety of skill set. So there are like 2 to 3 users that are really expert level. Most of them are like use it, in their class only, and then 1 or 2 users haven't used it before. Future directions. So for this particular project, we think there's still a lot more that can be done to improve this. First of all, how do we support a wider range of APIs, not just a plotting library of Python? And how do we find a representation that can encode the hierarchical structure? Right now, we sort of flatten out the abstract syntax tree to have a sort of back of code elements. But in reality, the dependency on the hierarchical structure may contain a lot of information that we haven't leveraged yet. And also find a better association between natural language and code, and encode API knowledge directly in a neural network model. So any question about this project before I jump to the next one? OK, so yeah, summary of basically what I said before. So this next project is programming by visual example. It's a work in progress. So it's more open-ended at this stage. It has very similar motivations as the first project, but it involves different inputs and outputs of the system. So again, programming is often inevitable when we want to create visualization, especially when it gets complex or it involves a lot of repetitive parts or interaction. And in this particular project, what we are focusing on is that is this particular scenario where the user has a visual example. Say I go to say I have a survey result, but I want to create this sort of divergent bar chart to illustrate the Likert scale item score distribution. But I don't know how to code this. I do find this example in one, say, related work that I really like. I want to re-implement this. It's going to take some time if I don't know where to start, and if there's no direct support in the programming library that I favor. So how do we solve this? Can there be a system that takes this image as input and generate a code example directly for the user? And how do we do this? So the idea is that we want to combine computer vision to understand the existing visualization charts, and language modeling, which serves as a code synthesizer to directly write the code examples for the user. This way, we think that we'll generate visualization prototypes faster and make it easier overall for the user, improve their productivity. So the roadmap is like this. We want to build an end-to-end pipeline that combines computer vision techniques and language modeling techniques, where the input is a chart image and output is source code that generates that chart. And of course, we want to leverage a state-of-the-art architecture where an encoder is a convolutional network that understands the chart image, and decoder is some kind of recurrent neural network that generates source code. The difficulty, though, is that how do we find training data for such kind of tasks? Because all deep learning models require an extensive amount of data for training. And the idea is that we want to find as many code examples that can actually generate images as possible. And then we want to generate augment these existing code examples by expanding and varying the parameters in the input space, the data space, to generate a large set of synthetic chart coding pairs for training. And also, there's really relatively little literature on evaluating such kind of automatic code generation, let alone based on image. So it's really uncharted water here. But that said, there are indeed quite a lot of related work in each separate component. For reverse engineering of charts, a lot of work in the HCI community. People have looked at chart type identifications of given a chart, whether they recognize whether this is a bar chart or pie chart. That is relatively more straightforward. It was solved quite a long time ago. Chart data extraction and chart redesign and regeneration are more difficult. It involves the system recognizing what a chart is, what type of chart is, and then to extract the actual, say, the actual data values from the chart. Say this is a bar chart with 3 bars. The system needs to know that this is 1, this is 5, and this is 3, and then and somehow restyle it for the user. So there are a lot of work on that domain. For neural network domain, a lot of active work is ongoing with image captioning. People have looked at the CNN plus RN infrastructure. And on the more traditional approach side, people have looked at retrieval-based or all of these other more human engineering heavy based approaches. For image-based code synthesis, this is like both involving this and this. There is a latest work that recognize an image, which is like a snapshot of an equation from a paper, and it can generate LaTeX source code. So it involves some kind of image to code pipeline. But it's different from our purpose because recognizing an equation and generate the LaTeX source code, it involves some linear sort of scanning from the left to the right of the equation. But there is some global structure, like there's a fraction. And in chart examples, it's really different. We need to understand the chart type, and we need to understand what kind of styling, and then the graphic elements, whether there's a legend or there's a title. So it's more different a problem. So here's our model architecture. We reused Karpathy et al.'s neural talk architecture. It's fairly standard nowadays, where there's a CNN encoder that understands the content of the image, and the RN decoder that generates the caption one token at a time. I want to show you some preliminary results we have gotten, and these are pretty interesting. So first is about training data acquisition. We acquired code examples from online tutorials, Stack Overflow, and GitHub. This is basically the same set of code examples we obtained for the previous project. And then we filtered these by the presence of graphing API function calls and expanded those by varying their parameters. So here are some examples. So given one simple bar chart, given one type of chart, which is bar chart, there are like a lot of variations that are possible. It can be simple bars, group bars, stack bars, and the background themes can be different. And then all of these graphic elements can be different too. So it's really hard to see clearly these source code, but the idea is that we vary the styles and the data and the number of elements that are present in each given chart, so that we have a lot of pairs between the images and source code. And then we want to first separate the testing of the encoder and the decoder. So we first look at whether the existing convolutional neural network are capable of detecting the chart types. For this smaller scale example, we look at 3 big major chart types: bar charts, line charts, and pie charts. And then within each major category, we look at 3 subcategories. So like previous example, for bar charts, there are simple bar charts, group bar charts, and stack bar charts. And for line charts, there are like simple line, multi-line, and so on. For pie charts, there are exploded pie charts or normal pie charts. And then we use the convolutional neural network encoder to get 768 dimension vector representation of each images. And then we use a support vector machine to see if these features can be sufficient for the classifier to learn a classifier a boundary between these image representations. So here's the example. So there's a confusion matrix between different charts. You can see that it does really fairly well. There are relatively little confusion between sub-chart categories. For example, single line charts can be mistaken as simple bar charts, but it happens fairly rarely. For within line charts, there are some major confusion, slightly more confusions going on. But we think that overall, this is sort of a proof of concept that the image representation can be reliable, at least to some degree. So here's
Does that depend on the colors chosen for the lines? Like, there's not enough.
well, for chart types,
I was thinking more like the multi-line versus single line.
yeah, multi-line, for some cases we vary the line colors. For some cases you can vary the marker types, or whether a marker is present or not. So there are a lot of variations, and we haven't really separated out the case where color is the only varying factor. Yeah, but it's a good question. So this is the same task but I visualize the chart vectors. Chart embedding vectors in a 2D space using t-SNE. So what this shows is that the distribution of all the charts in a high dimensional space that are further dimensionally reduced to 2D space. Each point is a chart, and the different colors represent different chart types. So as you can see here, this is maybe too small, but let me read it for you. All the green dots are bar charts, and all the blue dots are line charts, and all the red dots are pie charts. So visually, you can see that these are separated fairly nicely. There are some mixing here, possibly explaining the confusion between bar charts and line charts. And then you see the separation between within group. So some pie charts are here, some pie charts are here. And we dig deeper and then find out that it's really the theme that causes this separation. So we vary the themes. Some themes are light and some themes are dark, and it really plays a very important role in this case. So these are like dark themes, and these are light themes. So we need to keep this in mind further down building the entire system. Okay, so that was chart type recognition. And then we are interested in whether chart features can be recognized by the encoder. And in this case, we generate the simulated training data and synthetic training data where we vary the knobs where the grid lines can be either present or absent. Line width can be changed, line color can be changed, and whether the legend is on this side or this side, and so on. There are a lot of things going on. And we picked 10 chart features as the prominent features we want to test against, and we want to see that whether given the learned embedding vectors, a support vector machine can differentiate whether the feature is present or not. And to some degree, it is satisfactory. So the grid lines, line width, and line colors are really performant. But for more fine-grained details, like whether there's a title here, it's less sensitive. And right now we can only speculate the reasons. I think this is like every image is confined into 256 times 256 pixel space, and a lot of the smaller features are gone or like more obscure from the model's perspective. Sorry. And then we moved on to see how well the end-to-end pipeline works. So this involves, given an image, looking at how well the system-generated source code matches the original ground truth source code. And to use, so we use a fairly standard benchmark metrics, which are commonly used for machine translation and automatic summarization of natural language documents. And they basically break the ground truth into n-grams, and then see the precisions and recalls of these n-grams in the target generated source code. And then there are some different average themes going on here. So we compare the, so let's first look at this score, blue score. It involves 1 gram, 2 gram, all the way to 4 gram of the ground truth. On the most left-hand side here is the score we obtained by randomizing the chart vector representation. So basically, we consider in the pipeline, we did some sabotage by just introducing random noises here, and then see what kind of outputs can be generated. So this, and then we compare that with actually using the source code, the image, and this way we can tell whether the information in the input image is actually being leveraged and used in generating the source code, or from the other perspective, how well the source code is generated conditioned upon the information in the image. And we see the difference is very significant. And the performance between these are like different subchart types are relatively more or less in the close region. For this different machine translation metric, it confirms the similar trend as this one. But for this, we really don't understand what's going on here. So that's sort of an ongoing inspection. Normally, this score is the higher, the better the performance of the system. So that's something we're still actively investigating. And here, we want to understand how well a general domain model, let me hide it for a moment. So I want to understand how well a general domain image captioning model will perform on this. The idea is that to inspect what is the limitation of these RNN decoders. So let me first show you some results we see. So all of these are obtained by looking at how well a model it performs when the model is trained on MS COCO images, which is a general domain data set. And there are like all kinds of humans and dogs and cars and so on, but there are no charts. So given this bar chart, it shows a bathroom with a bunch of urinals on the wall. So we see that it's pretty funny, but it does capture the sort of the pile structures on the grid structures on background. So it may indicate that this is a bathroom. View of window in the dark room, it matches the theme structure. So toothbrushes and so on. It's interesting. On one side, it tells us the model does capture or successfully conditions the decoding process on the visual features of the input image. But on the other side, it also tells us the constraints of the model, this kind of model. No matter what information you feed into the model, it will generate something that reads like grammatical English. And on the other side, imagine that we train this using source code. So no matter what kind of visualization we provide as input, it will generate some kind of grammatical Python source code. But does it really generate that image? It's an open question. I mean, the model will pretend that they know what it is doing, but it's actually not knowing. It's just imitating whatever distribution is in the training corpus. So this is the idea of this page.
I got a close-up of a red and white sign, and there's no white.
That's right. And we actually look at the input distribution. Red and white is a popular trigram. So red and white, this phrase occurs a lot. So whenever the user, the model generates a red and, it just wants to generate white because I've seen a lot of red and white as a phrase. So this again exposes the same problem that the model is just imitating whatever distribution the training data has. Okay, so some upcoming work for this particular project is that we want to generate training data with more variations that cover a lot more variety of chart types and variations that partially will solve this data sparsity problem, like this red and white problem. We want the model to be really looking at the signals in the image, not just dreaming or like recalling from memory. And also we want to use empirical experiment to determine which metrics really can evaluate how good a synthesized code example is. Right now, machine summarization, machine translation metrics really don't serve well to the need of evaluating programming language. And also, we want to potentially integrate image to code with CodeMan. So then the workflow will be given a visual example, feed it in, and the system generated code example, and then you can use the natural language to modify it. So then it will be an expedited workflow for generating any kind of visualization. That's it. Thank you. One minute for questions. Yeah.
You mentioned that the images in the second part are 256 by 256 pixels, and then from it you have something like 768 dimensions. Can you say more how you get from a pixel to dimensions?
Right. So the pixels are like live in a 2D space, right? You have 250, 256. The 768 dimensions are the 1D vector representation that represent that image. So it's you can consider it as a projection or like a mapping from a 2D space to a 1D space. I mean, no, actually 768 dimension space.
So you're using something like PCA?
No, that's what the embedding part, the neural network is doing.
Okay.
Yeah, using PCA, it will give you very poor performance because it only captures whatever the dimension has the biggest variance. But with neural network, it learns a lot more about the relations and the similarities between the training data, and then the underlying structure that exists in that 2D pixel space.
Come to my tools and tech in February. I'm going to be talking about convolutional neural networks in details.
Yeah, go to his talk. All right, thank you.